Hello, good morning. Thanks for joining me in my shop here for day 2 on this PYE radio that I'm working on. And great thing, yesterday it turns out the radio is actually in wonderful working shape. So today I'm hoping to do the alignment on it. But first, there's a couple things I really would be wise to check, even though the radio appears to be working quite well. And one of those is output tube bias, and maybe plate and screen voltages throughout the radio for those tubes that have a screen and the like. I don't expect to find anything funny here, but maybe. In particular, the grid of the output tube is a particular concern. The blocking capacitor that's protecting that grid is weak, then the grid may be pushed positive, and you can't really tell that when playing the radio. But in effect, you'll be cooking the output tube. So, we got to figure out which one of these capacitors is that capacitor. Pretty sure that's the output tube right there. This looks like a rectifier tube here. So, and what is it? 6AQ5. 6AQ5. Let's take a look at the schematic and check about the way this tube is in the circuit here. Okay, here's the output tube here, and the grid is there. This is the capacitor in question right here, right from the plate of this tube. So I should be able to find the plate terminal, find the grid terminal, and in between it is this capacitor. Looks like C40, 44 or 46 or something like that. C44 is 0.01, 46 is also 0.01, and that's typical for this kind of capacitor too. Okay, so we'll try to find this underneath the radio. Okay, so the tube is right up in here. It's bound to be maybe this guy right here. And my speaker connection right in the way there. So we'll take a look at 6AQ5. Depressing day for cats because it's 1 degree outside. Bit of snow fell. Poor cats, very depressed. Everybody's depressed now. 6AQ5. 6AQ5A has a controlled heater warm-up time for use in television receivers employing series connected heater strings. Well, I don't think that's a television, so I'm not going to worry about that. 6AQ5. So the pin we're concerned about is pin number 7. That's the grid pin. Should be fairly easy to spot. And we're going to want to make a measurement on it. Grid. We have to look at the schematic again and see how they handle the B minus on this radio. Let's take a look again. So there's the B minus. Now the question is, how is it connected? Well, it's solid to the chassis, if that's what that means, and that's almost certainly what that means. It's showing one single connection. Is there any other chassis connection in here? I don't see anything else with that ground symbol on it. You'd kind of think they would do this with a capacitor, but they haven't. So I wonder if we could actually find this spot. This might be very hard to spot in the radio, but I don't see another single ground, especially out here at the front end. Sometimes they're doing a little different grounding of things out here. No? This big bar here, is this part of the... It is. Look, there's a light wire shown here. Maybe they should have drawn this in heavy through here. All B minus. Okay, it is what it is. Wait a minute, whoa, stop for a sec. Where's the heaters? The heaters are not showing up here at all. And here we show the, this is almost certainly what's feeding the heaters, and they just show an arrow. So the other side is right to the ground. So the heaters are fed, probably every heater, one side is right to the chassis. I wonder. There's really no indication, is there? Usually they have a little heater diagram somewhere. There's nothing here. Well, we can eyeball that. We'll look for one of the socket terminals being soldered right to the chassis on these, and they're all treated the same. Every one of them, except for this one, of course. This guy has his own winding. Okay, so I think I'm gonna take a look with the close-up camera. It'd be easier for me too, because there's a bundle of wire up there. Pretty hard to see past it. Okay, so that's the socket there. Get a little more light onto it here. Okay, well, right away we're looking at pins. Pin 1 is not connected, and pin 7 is right there. And sure enough, it's that capacitor I took a guess at. Ooh, it looks fantastic, doesn't it? So this would be the plate over here, and I'm willing to bet that orange wire is, well, I don't know what. See the way the dust is built up on that darker orange wire center of the screen, and dust is kind of stuck on this resistor and the lead and all this stuff. It's all indicating high voltage. All the stuff with dirt. Like if you look there, you see going across a clean orange wire, and then below it you see other orange wires. They've got dirt on them. That's the electric field doing that. Yeah, so you can actually measure the voltage by the amount of dirt on the wire. Oh yeah, what's that? That looks like I think that's a capacitor. Okay, but anyway, what we're looking at, what we want to know is the voltage on this pin, and the other thing is we want to try to find out how they're dealing with the ground. Looks like a couple bare wires just soldered right to the chassis there, right there. So one of them, I'm going to guess, goes up to the heater terminal, out of view back there, but we just can't really get a good view of it. But well, why two wires? I'm not sure. Two bare wires. Now let's look at another socket here, one that's easy to see. Here's one. Oh yeah, there's the wire going right to the terminal. Right through the center post. And then over to this terminal. Yeah, so they're all treated that way, I'm sure. They would have to be, wouldn't they? Here's another one. There it is again, soldered to the chassis. So heater current's flowing in the chassis, but not much else. All these tubes have cathodes in that, so the actual sort of radio or amplifier part is operating independent of the chassis, except for one single connection, which we will never spot in here, I don't think. Okay, so that's easy. That's easy. Nothing scary here. So we're going to try to read the voltage on this guy, and we can do it with my vacuum tube voltmeter here. That's this guy. Put him on. So in the long run, what I'm hoping to do with this radio is bring in my other PYE radio, take it out of its cabinet. I'm thinking of refinishing both cabinets. It doesn't look like a big job at all. And then have these two radios in here. One, I believe, is the earlier version of the earlier version of this. My other radio is the earlier version of this, I believe. I think it'd be a lot of fun to compare the two of them and see what can be seen. So we need to turn this guy on. On. Away we go. Dim bulbs. You know what? I did not look. I gotta look at that schematic again. We'll let the radio warm up. I gotta take a peek at the schematic because there's that pop we heard before too. Single pop. I need to look at this right here. So this is how this tube is biased. It's biased by this cathode resistor. So we can check the bias by measuring the voltage here on pin. Oh, pins are numbered. Pin 2. I can't read the number there, but that's supposed to be pin 1. So we should really see pretty much 0 when we check this with the voltmeter. Okay, and you can hear the radio operating, so let's go back. Okay, lots of things to check here. How about B plus to start with? So the filter capacitor's down here, and I think I can just, yeah, let's put this up. 500 volts, and we're feeding the radio low right now, 92 volts. So let's see what we got. Right on the filter capacitor here. Why so noisy? 150 volt scale. Full scale now. Oop. So a little over 100, but you know, we're way off here. Let's go up with this. If I'm going to make these voltage measurements, I should try to have this correct. So we're going to knock off the dim bulbs. 106. $117 volts. Good. Now we'll take a look at what's happened to the B plus. Notice the radio didn't change much in operation. Didn't appear to change much. I think the volume's way up. What change here, boy? Big change. 250 volts now. There's a huge variation on the plate or on the supply voltage. 250 on that side. What about this right here? A little less, 200. And there must be a resistor in there, a high wattage resistor. Can't really see it. Okay, let's turn it down a bit here because we're going to go on the grid of the output tube. And we're going to look at the high side of the blocking capacitor. So we should be looking at the plate voltage of the tube previous to the output tube, right here. That's nothing too exciting, is it? 70 volts. Well, you know, that's possible. And I think there is a table. There's a table I can go through. I was looking at it earlier that shows voltages on these tubes. Just not sure I can interpret it right. So now we're going to go after the grid voltage. This might be noisy. Not very. So I saw a positive value on here. Not sure if that's a good sign. Positive to ground, eh? 6 volts. Positive to ground. And now we want to read the volt bias drop on the cathode. I don't know what cathode is. 6AQ5. Don't know that part of the alphabet very well. 6AQ5. Cathode is on 2. 2, we should find some positive voltage on 2 that actually represents the bias on the grid. Positive voltage on 2. Ooh, a little hard to get in there. Holy smokes. Pin 2. Very tricky. Pin 2. Wow, I'm not sure what to make of that. There's something weird in there. Let's look at the other camera. The radio's operating now. I'm going to be just a little conscious about what I'm doing with this camera. What I'm looking at, so you see the wire with the braid. And the braid goes down and it just skips around that resistor wire. Oh my gosh, it sure looks like it's in contact. The braid obviously is going down to the chassis. I don't think that resistor is headed to the same place. I'm not sure what. What I'm really trying to see though is terminal number 2 or pin 2 of the tube underneath there. Oh, scare me. So pin 2. Oh, it's so hard to see in there. I think the ground wire you see in the background is going to a different terminal and a resistor. And that, wow, that is just barely clear there. You could make that into a short pretty easy just by moving, just by wiggling some wires here. Oh my gosh, that's crazy. And I just keep looking at it because I can't believe it's not shorted. Okay, so if that's pin 2, that's the cathode, and that resistor is probably the cathode resistor. The value on it is it's red. Ooh, kind of looks like red, purple, brown. I guess that would be 270. That's just the kind of thing you have there for a cathode resistor. Okay, making some measurements now. Expecting a low voltage here. Don't, just careful. Well, 15 volts. So we've got 15 volts, but there's 6 positive on the grid. So I think the grid, if we were to measure it from cathode to grid, we would find something like 7 or 8 volts there. I'm not going to. I can't use the VTVM for that. At least I would never try because it's one side's grounded. I'm going to use this meter because it's not grounded. You can read from the grid to the cathode. I'll put the. Let's think about this now. The grid is supposed to be negative, so I should read it. Cathode grid and get a positive reading here. The cathode should be positive to the grid. Okay, so it doesn't really matter. Just makes the minus sign not show up. That's about all. So now, so we want to go and have my fingers on the chassis here while I do this. Go there, and then the other one. Somebody look at the meter for me when I get this in here. What's it say? Why is that light flashing? It says 0. Come on. How can you say 0? B plus test. And this very noisy radio. B plus test. What's happening with my meter? it's not the meter, it's just me making a bad connection. Okay, back to the reading. Negative on the grid, positive on the cathode. Negative on the grid. Here we are, minus 2.6. So that's the true bias. Minus 2.6. Minus 2.6. That sounds way low. Cathode resistor is trying to put 15 volts onto that grid, so to speak. And the leaky, what appears to be a leaky grid blocking capacitor is trying to put 300 on that grid, and they are fighting it out. So the grid is still negative, 6BQ5, 6BQ5. Why am I closing this book all the time? 6BQ5. 6. Okay. Come on. Where are you? What happened? 6. I've gone totally nuts. 6. 6. Okay, just lost my mind here temporarily. 6AQ5. 6AQ5. That's what it is. Not B, it's a 6A. 6AQ5. Yes, I did lose my mind, but I found it. 6A. Well, I found enough of it anyway. Okay, 6AQ5. What are we trying to do? I totally forgot what I'm up to. Oh, we want to know the grid bias. Grid bias. Typical grid bias. So we're looking here. Class A, Class AB, and push-pull. All listed together. Maximum ratings. Grid number 1. Grid number 1. Where? Go here. Maximum circuit values. Grid number 1 circuit resistance. Cathode biased operation. 0.5 megohm maximum. Well, that's the grid grid leak resistor. That's not. This is not showing me what the grid voltage is supposed to be. Oh, grid number 1 to plate. No, those are capacitances. What's happening here? Grid number 2 input. Oh, they've given a grid. They've given a graph for this tube to interpret this graph. So we have different grid biases here. The highest one is minus 30, and they have a grid bias of minus 5. Grid bias of 0. And over here they're showing the plate current. No, plate current for, yeah, and then down here they've got the plate voltage. So I know the plate, we don't know the plate voltage. What do I got? Plate, maybe I measure the plate voltage. Plate voltage, I'm going to guess it's 250. So we're coming up here, we're biased way up here. So at this bias level, you're talking 100 milliamps flowing through the tube, just sitting there. But if they were to bias it at minus 15, you'd be talking about 75 milliamps, even less. And for some strange reason, they have a little 12.5 piece of this chart in here. Why would they just draw a little tiny piece of it? Because they couldn't write the number 12.5 over here. There wasn't enough space. But what's the significance of 12.5? Is that the ideal? How come you don't tell me this? Because they have the chart and they think you're smart enough to figure it out. Well, I think if we change that capacitor, that grid voltage will show up around the same as the cathode resistor drop. That's what I think. So that's good. This is a good experiment here. Let's do this. Okay, I'm trying to turn off the computer. I really want to turn off the radio. I get a little excited in here sometimes, you know. This is kind of neat. It gives us a chance to really see you know, in the field, how things really work. So this lovely looking capacitor, the suggestion is it's actually leaking. Okay, so he's coming out. We're going to test him right away. He's making a run for it, in fact. A lot of these capacitors make a run for it, I've noticed. Let's take a close look at the condition of it. I think this is a good chance to learn some stuff. So I declared this to be a good looking capacitor. It's just covered in wax. It goes way up the ends. The other end looks pretty sealed. It all looks really, really good. Except for the fuzzy stuff. Oh, there's a bit of a dig there. So it's been laid up against another component. It's disrupted the wax a bit. Okay. Let's give them the treatment. So I think modern capacitor checkers look for something a little different than these older capacitor checkers. Look for concern today with capacitors isn't so much can they take hundreds of volts. That's not quite the concern. So a modern capacitor checker measures a few other factors which I think are more important in the miniature world of capacitors. That's not being miniature. Today's miniature world, I think there's trouble with current flow in conductor leads or leads and stuff like that. That just really don't happen back in the old days. Okay, I'm going to put 50 volts across it. I'm going to watch the magic eye here. While the capacitor charges up for half a second or so, the eye will close, indicating current is flowing into the capacitor. Then when the current stops flowing, the eye will swing open and sit just like that. Oh, that was the wrong switch. Yeah, I am too excited this morning. Okay, 50 volts. It says 25, but it's really 50. Here we go. Okay, so this is indicating a fairly leaky capacitor here. The eye is just barely cracking open, which on 50 volts indicates this is a poorer than average pour. Good looking. You know, you can't judge a capacitor by its wax. I guess that's the part of the lesson there. So, yeah, is that potentially leaking charge onto the grid? Yes, it is. It is. It is. So the story is hanging in. Now I gotta get a 0.01, stick it in there. 0.01. Going to be a 0.01 that can handle the higher voltage. 1,000 volts. Ooh, that's a big honker. Now this is the style that's really supposed to go onto a board, but it doesn't really matter. I want to use this. I don't know if I want to use this. It's quite a stretch between the two terminals, so if I use this one, I have to put extension on it. It's 0.01. What am I doing with 0.05s here? 0.01. I have some with some really long leads. These ones here. They look like super high quality capacitors, but these are old. 400 volt. Look at how long the lead is. Wow. Let's check this one. Well, this is a vintage capacitor. It's a NOS, new old stock. It's never been used. Just been sitting around, but that doesn't necessarily mean it's any good. Okay, so same test. 50 volts, watching the eye. Popped right open like an explosion. 250 volts, right open. So there's no leakage in this capacitor at all. Let's just give it a moment to discharge. A little more. Then we're going to measure its capacitance using this. So 0.01 is going to be on this scale. Okay. Now we just swing the arm. I watch for the eye to pop open. Oop, there it is. Pretty distinct. Where is it popping open? That's 0.01 written right there. So there we are. So I have I know these capacitors are good because I have a number of them, and I've had a number of them tested just like this on occasion. These are really good capacitors. You know, this is 40 years old and it tests perfectly good. It's going to be 90 years old and still testing perfectly good. I don't think I will be. No. Well, it took a little longer than I expected. Just a little hard kind of working in the angles there, seeing what you have to see. So we're going to repeat the test and see if there's still, we'll see what kind of voltage we get on it. Okay, everything's ready? Yes. Okay, dim bulbs to start. Good. $118 volts. Okay, so on the 15-volt scale, and we'll go right at the grid where we got a +6 voltage last time because of the leaky capacitor. So did the meter move? Didn't move one bit. The reason it's not moving is because there's a resistor hooked up to the grid that goes to ground. It's a high value resistor, so it doesn't discharge the grid seriously. But in terms of a few coulombs of charge, it will discharge it and hold it at zero potential. There'll be virtually no current flow through it. So yeah, there's always a leakage through a capacitor, but we're talking about, you know, individual charges, that kind of level. If that resistor wasn't there, the grid would begin to float, and it would eventually float up all the way to the B plus of the other two, even if that capacitor is good. Well, that might take a long time. That's good. So that's good. So we solved a hidden problem in this radio. There'd be no way to know that that's happening without doing these tests. And the benefit is my 6AQ5 is going to run much cooler now, and chances are we're in the characteristic curve. We've gone from kind of down to low here to up into the flat area. So that means under high volume, when the signal widens out, it's still operating in the flat area. It's not going down in the curve here like it probably was, or going up too high and hitting a cutoff. If the tube cuts off, that would not sound good at all. Great. Now what else should we do to this before trying an alignment? Is there anything else? Looking at B plus voltage and the screen voltages of the tubes everywhere, all the tubes. And maybe we can track down some more problems that way. Again, problems that don't really present themselves except under maybe more extreme operation, like high volume and stuff. Okay, so I'm going to study that chart with the weird headings that I don't quite understand, and then we're going to get busy on doing that, doing those tests. Okay, so I figured out what these odd codes are here. EA, IA, ESIS, EK, 1K. I looked on the internet, I couldn't find anything, of course. Kind of an obscure thing to search for. So I just started looking at it and analyzing it. I guess, well, these are the highest voltages. These must be the plate voltages. And then I thought, wow, 70, 70, 70. This looks like screen. Then I thought, oh, A is anode. E is volts. And the whole thing came through. Volts anode, current anode, volt screen, volt cathode, current cathode. I got it all. I don't think I'm going to measure any of these currents. So we have plate volts, screen volts, plate volts, screen volts, and cathode volts. Oh, that's interesting. So there, right there is the voltage we read at, wow, so minus, wasn't minus, I thought I read it around 15, and this shows it to be 9 on the cathode. But you know what? There's much less current flowing now. Hey, let's check that. I didn't check that before. Cathode. Cathode voltage. So it's cathode, it's from cathode to the chassis. It's fine. Okay, so we can use this meter over here. And the radio's still on. Yep. If you're wondering what was it, how did I tell it was on when I did that? It was a tiny little click came out of the speaker when I touched it. That was, I wasn't feeling voltage there. So yeah, 15 volts. So we're ready. So on the cathode was right over here. This almost shorted. So now we're reading. Can you see it on the meter there? 9.5 volts. Oh my gosh, it's right on the money. Wow, we really settled that down, didn't we? Changing that capacitor was a really important step. Completely invisible to the operation of the radio until it's too late. And there could be more of that stuff in here. So we're going to look at the, now unfortunately they haven't written down the pin numbers for any of these. That's really a hassle. Why wouldn't they do that? Okay, so I got to stop for a while and sort a few more things out here. Great, so what I've done is I've gone away and I've marked the pin numbers for all these different tubes, and I'm going to go ahead and do the tests on it, and we'll see if any of these vary from what they're supposed to be. But I'm going to do it off camera because it's a bit of a fiddly thing. Okay, so I was just getting ready here to make some tests when I remembered, oh my gosh, that's right, the switch in here, the contacts are terrible in it, so I have to clean that first. So that's what's coming next. So I'm spraying in some cleaner here on the switch. I'm getting gassed out very quickly. The set is off because you can start a fire doing this kind of thing. So I'm really soaking it down because I know there's a lot of trouble in this switch. The reason I know you can start a fire doing this is I've done it. Okay, let's hope that's enough. I've got the WD-40 at the ready here, but I haven't sprayed any in there. It's probably dried up enough. Okay, power on. Go back to the AM band, that's where it is. We'll see how reliable the switch is first. Oh, I almost forgot to do that. That's a bad thing to forget. So we're on the broadcast band, and hey, it's making some sound. Just go up through band after band and see what happens. Okay, now we can wheel the switch. Good. Next band. Next band. A little quieter. Good, that's pretty quiet on the higher bands, but that's me, that's the wrong wire. Yeah, wrong wire. Good. I think the switch is reliable now. Good. Now, carry on with the reading of the voltages. Let me do the first tube. I'm going to do the output tube first. Output tube is here. Pin 5 on the plate, 226 volts. So 250 is straight up on that meter now. So 226 is just less than straight up. Output tube up here. And good luck on pin number 5. Oh yeah, right. I don't know about this. It is completely blocked in there. I don't see how I can possibly get up in there and test it. I have to put a tube extender in the top and work on the top. Well, there you are. There's the first one. Okay, pin number 5 and number 6. And both, well, 6 is probably, I can probably get the 6 here. Okay, I see it. And what are we looking for? Pin 6, 198 volts. So 198 volts is going to be right around here. There it is. It's right on the money. It's right on the money. 198. Excellent. Okay. Let's try another one. Go to the top of the list. The RF amplifier. Okay, 6BA6. I don't have a tube position guide. So there's a 6BA. There's two 6BA6s and a 6BE6. They all look the same, pretty much. Can I read any of them? Okay, so that's a bit of a problem. Gotta figure which tube is where. Oh my gosh, really? Luckily, I remembered there's a tube layout chart inside the cabinet there, very faded, but not so faded I couldn't read it. So, I just replicated it here. So now I have a tube layout chart. This is viewed from the top, so you have to kind of look it up that way. I know which tube's which pins got what voltage. I'm ready to go. Okay, let's take a look at the result here, and I think there is something worth pursuing. So we'll look at the plate voltages that appear here. So, you know, it should be 93 measured 100, should be 150 measured 140, should be 197 measured 190, 197 measured 200, 70 measured 68. Couldn't get the plate on the output tube. It's just the pin is buried. Those are all fine. I don't see anything there to get concerned about. Now if we come down the screen voltages, so the screens, these three tubes should have a screen voltage of 70, 70, 70, but they've all got the same 55, 55, 55. 55, 70 on a screen. We can look into this. There's going to be one component that's causing this on all three tubes. So find the one component, almost certainly a resistor has gone high. Find that resistor, change it, these will be correct, all three. We get a 3-for-1 deal on that. This is the output tube. Screen should be 198 measured 200, that's fine. So, and I didn't bother with any of these. So it's just a screen and the plate I'm kind of concerned about. So let's see if we can figure out what might be causing this problem here. What do all these tubes have in common? And it's very, very regular for a radio to have kind of a shared screen supply, if you like, with some big capacitors on it usually. So let's go look for these. Okay, and we're going to do that on the schematic. Okay, so the tubes involved are V1, V3, and V4. So V1, V3, here they are, all nicely arranged here. This must be V2 down here. Yeah, it's not part of this picture. You pick any screen and follow the wire. You see, they all have exactly the same wire going to them. Okay, so we'll follow it back this way. Here comes a resistor. Da 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 da. R7, right off this switch. Just quickly looking at these notes here. No problem. R7, we need to find out R7. So R7 is, as I say, 15K, 2 watts. It's a 2 watter. Want to bet it's one of those hot resistors? It looks like 15K. way we would recognize it is it's tied right to the switch here. This is the tone switch, isn't it? This is the band switch over here, and this is the tone switch. So they're fooling around with the screen. Oh, you know what's going on? There's a phono setting in this radio. Is there a phono setting? I don't think so. Let me look. Let me just quickly check. There's a terminal on the back, and let's get the right knob here. And the knob has, that's the tone knob. Let me read you the tone knob here. The tone knob. A little hard to see on the camera. So this says gram, G-R-A-M. And then it has MEL, and it looks like F10, but it certainly isn't F10. ME, I don't know, two tone settings. Oh, it keeps going. So here we are, short wave, or SW, it must be short wave. Then we have MEL, what's that, melodious? And we have BRI, bright. FID, fidelity, and off. So you click it on, you're in fidelity mode. Then you can go to bright mode, which must kill the bass. Then you can go to mellow mode, which probably kills the treble. Then you go to short wave. For some reason they have, I don't know what they've done for short wave. And then we get to the gramophone, and you've got melodious, and what was that last one? Right? No. Fidelity, melodious, and fidelity. I don't know. Well, you had to come up with names for tones. You know, tone. No, that's not the one I wanted. I wanted to look at the band switch one, which is actually on the radio here. Why is there no? That says tuning, and this other one says wave change. Oh my gosh, doesn't say anything else. But there's nothing on the cabinet. I'll have to go get the knob from my other radio. Well, I'm guessing one of these settings is phono. That would be the very quiet one, if there is one. So, I don't know, that's broadcast. Can go farther this way. And you know, that's got to be the radio's still operating here. I don't know how you get phono going on these. Some of these sets you literally plug the phono in. It kind of nulls out the. Oh, maybe this has got a switch. So some of these phono plugs have a switch built into them, and there's a very long, funny looking, really long prong comes in and will separate a switcher, but not this one. Bottom line is, I don't know what they're doing with the phono here. And there are radios where you have to tune between stations to listen to your record, because the radio is still playing while the record's playing. That's kind of crazy. Doesn't make a lot of sense. Okay, so where are we at? So we're hunting down the 55. Why am I staring at this now? I don't know. Why did we come? I can't remember. I've lost my mind again. Let's go back to the schematic. I think I left it back there. Right, so I was going to hunt down this resistor. That's what I'm trying to do. And it's going to be right off this tone switch. And can we tell which wafer it is? S2B, S2A, S2D, S2C. Now, somewhere do they help you figure that out? Let's say A towards the front. Our gang wave change switch, band change switch, shown in fully anti-clockwise direction. So it's in the broadcast band. Tone switch, that's this one, shown in the fully anti-clockwise direction, which is off. We've actually got the radio switched off on this diagram. Where's that happen? here. So they don't really show that this is tied into this. Shame on them. So it says S2, which is all part of this, S2. Well, it doesn't help much. So the thing to keep in mind is, though, that in this switch, this tone switch, which you shouldn't be too afraid of, yes, you should be afraid of it, because it's got the power coming up into it. Somewhere. Oh. Really? Is that really how this works? Yes? Well, I'll show you. I'll show you what's going on here, because it's good to make a note as to where these 120 volt wires are coming, and that would be before I find out the hard way. Actually, it's the easy way. Just get a shock. So on the back of the tone switch, you see quite a switch sitting there. There's the power cord coming right in, right to there, right to there, right to where you could easily stick your finger on that, really easily. And the other switch. Yeah, so I guess the switch poles are like this. The interesting thing is, when you turn the set off, there's no power getting anywhere in this set. It's dying right there on the switch. Okay, and so yeah, here's a resistor coming right off the switch. It's right here. It's right here to be seen. Let it be seen. So would that be the guide? Now, body and dot. So it looks like brown, green, orange. So it's something, the dot is orange. So it's in the thousands of ohms. 15,000 was what it was. Exactly. Brown, green, orange. That's 15K. Or is it? Okay, power off. Power off. Resistors, in my experience, tend to go high. As the resistive component breaks down, it increases its resistance. It doesn't go less. Sometimes the problem can be maybe where the lead is connecting to the resistor. This is a carbon rod resistor, I'm pretty sure. So it's just basically a carbon rod with wires wrapped around the end of it. You can kind of see them right there. And that's the connection. And then the carbon rod, the longer the rod, the bigger the resistance. The diameter, bigger the diameter, lower the resistance. And the longer the rod, the higher the wattage. Pretty simple stuff from back then, way back then. So, oh, that's got the spider in it. That's what it's been all along. And I get the spider out. I meant to get him out earlier. Come on. Oh, was one leg. Here's the rest of them. Oh my God, he's hanging on. He's hanging on. That's a pretty scary looking thing there. Okay, and what am I going to do with it? I'm going to put him in the garbage can. And of course I missed. It's on the floor now. Well, we'll just read the resistance using the ohmmeter here to start with. It's in the circuit. I didn't really make note of whether you can do this accurately or not. See what we get. Just back up a little bit. Lead there. The other one back in here. Ooh. Well, that looks like 1,300. That'd be like a 1,500, not a 15,000. And the other resistor here is not connected to the switch. It's got to be this guy. It's got to be brown, green, orange. He's got green here too. It looks like orange. Is that another same-sized resistor there? Just to confuse me a bit more. And what is the terminal it's going to? It's a terminal on a terminal strip. So it's not going to the chassis or anything. Well, there's still spider legs up here. Didn't he take, that spider's got a lot of legs. Well, I can nip it out and test it again. Or move this switch around and see if we can get a better reading out of it. That's not much better. So we can't get any higher than 1.2. How's that ohm meter? Which giving me trouble these days. What you do is you just wiggle this control until you get the reading you want. Hey, that's a real problem with human beings. Over 20K now. What happened there? Fixed it. Well, I am looking for this resistor to have gone high from 15K. So maybe it has. 30. Oh, it's exactly 30. How suspicious is that? So you're reading across a resistor. If there's a parallel circuit, your reading can only go lower. It cannot go higher. If it's going higher, the resistor itself must be carrying it up there. So let's nip that guy out. He's overheated anyway. He's done his duty. We're going to nip him right out and test him. Oops, 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 oops. What am I doing? My cutters are out of alignment. Got him out. Here he is. Okay, we'll make a reading right away. I'm going to switch to better reads for this. $18 instead of 15. My guess is 18 is enough to throw off that voltage. Now what about the other one that's up there? The other one. They're connected together. It should be easy to spot on the schematic what that other one is doing. So the one is here, and the other one, would it be this one, R4? R4 10K, 1 watt. No, it's another 2 watt. It's like, oh, I can't read this. Looks like there's a million 2 watt resistors in here. Okay, but probably not R4 10K, because I can see the green. It's a something 5 something. It's more like this one, R3. It doesn't look any different than the one I just took out. The one I just took out is R7. It's shown as a 2 watt. Well, that's clearly a 2 watt there with a 5. R21. This must be it. This must be it. R21. Now where's R? So can we find R21 attached to R7? Oh my gosh. There it is. Is that 21? What's it doing way over there? R21. Is there another one that could pass as R21 from the end of this wire? Tracing again, going this way. That's not 21, and that's the end of the road. Is there any other way we can trace from here? From here. Go back this way. No, this is through the switch. What I saw, the leads of the resistors are tied together. So it's got to be, oh, could be this one, R18. No, because what we're looking for is R21. You know what, this is R21. So there he is there, and he's supposed to be again 1500. So we'll measure that one in the circuit. Well, this has turned out to be a lot more interesting than I expected it to be. Try it with the clip leads here. Well, that's 1.5. Okay, 1.7. 1.68. I don't think that's enough to worry about. I think it's just this one. And we need to deal with this guy here. Okay, so we need to get a proper 15 and put it in there. Well, it's a little bit of overkill, but here's a 5 watt 15K resistor. Considering the 2 watt was hot, this might be a better choice. It doesn't mean it's really going to run any cooler. It's still going to dissipate the same amount of energy. So I really think when it says 5 watts, it's really telling you what it can tolerate. That's not promising you it'll stay cool or anything like that. This is also a wire wound. This is a wire wound resistor going in place of a carbon resistor. What was that resistor doing? It's in the screen circuits. Wow! If I put a wire wound resistor in there, am I running the risk of setting up some weird oscillating thing in a screen circuit? Well, maybe the answer to that is yes. I don't know. In some cases they very much come out and go, make it a carbon. And I think what they're really saying is don't stick a wire wound resistor there. But nobody told me that here. We'll stick one in. I would imagine if you ended up creating that kind of problem, that wire wound resistor causing some kind of oscillation or something, it might be really tricky to suss that out on a troubleshooting adventure. So I have another radio I have worked on. It's out in my garage. I've worked on it in here for a while, and it's a shortwave radio. On the 2 higher bands, the oscillator will not oscillate no matter what I try. That's why it's sitting in my garage waiting for me to come up with some new approaches. And there are certain kinds of problems in these radios which are really tough to nail down. One of them is the bad ground. You're supposed to have a ground somewhere and it's bad. That can be really hard to find because the effects are all over the place. And let's say you have 3 components going to a grounded terminal. They're all going to ground and they don't care about each other at all. You lift that ground and all those components start seeing each other for the first time. You got new circuits never before dreamed up. You got signals going places engineers never wanted them to go. Voltages going places. I lifted a this didn't solder very well. Bad ground, very, very difficult to find. That's my experience anyway. Come on. Give it more. Well, it's clearly got soldered because it didn't fall off during all this monkey business here. Let's try that and get a lot more solder onto it. So the purpose of solder is really to shield the 2 conductors from the from the atmosphere. I believe that. Of course, it has some secondary benefits, mechanical benefits in that. But mainly what you're doing, I believe anyway, is you're trying to shield the connection from the atmosphere. Okay, now over you go. And I did the easy one first and I left the hard one for a second. Not really. Okay, we want it out on its wires a little bit. The heat will then not travel down the wire to the lug, which I think was part of what was going on here. There we go. Got that clamped down. Now this change probably won't be apparent in the operation of the radio at all. Maybe if we knew some very particular way to become aware of the state of affairs with the screens, we might detect some little bit of a change. A little worried I was going to burn my finger there. Okay, did we succeed with all that? I think so. Put this down a little bit. That's really the only thing that came out of the voltage testing. So run the radio and see now if we don't find 70 volts there instead of 55. Okay, radio ready. I'm going to go through the dim bulbs here because we made a change. Oh, they're behaving normally. Okay, give it a full shot. Get my voltmeter ready here. Okay, I can hear the radio. Good. So I think it was right off on these orange wires. That's right. Okay, so we're looking for 70 volts, 150 volt scale. So basically straight up would be a happy thing. Let's try right up here. Ooh, okay, let's not try there. Let's try over here. Look at that. It's right on 70. Regardless of that other reading. Maybe the other reading I did it backwards. Let's go on the other side of the resistor. You did it backwards. 70 right on the money. Another good thing. So, you know, when you think about it, an awful lot of the circuitry in here is simply to set up the operating conditions for the tubes. Now, a lot of this is just around getting the tubes to operate just right. So in the course of doing a radio repair, and I'm not suggesting I've been a good boy about this, you know, I'm learning too. a good thing to do is to verify that all those that condition for the tubes to operate in is really there. Right plate voltage, right screen voltage, right grid bias voltage. Hunky-dory. Well, I think we're hunky-dory here. Now what about the grids of all the other tubes? We'll look at the schematic briefly, and I'm not too concerned about them. Let's just look at the schematic and see how they're done. And we'll pick up this grid. This is probably a large resistor here. Cathode going straight to ground. So this is probably picking up a bias, either self-biasing, or this will lead us to a bias voltage. So here's another grid. You know what it's going to lead us to? The ABC, of course, of course. We're getting closer to it. This is probably a very large resistor here. We're coming over. And there it is. So what lies here is the rectified output of the IF. So here's the IF amplifier, signal going through the transformer, coming over here and going through these diodes. So the output of the IF gets rectified. Then, you know, when you rectify an AC circuit, you get a AC voltage, you get a DC voltage out of it. And that's what's here. And then this becomes the ABC voltage to run the radio on. Well, somewhere, I lost track of it. Somewhere in here. Somewhere. Not every tube is affected by ABC. Different radios do different things. Generally, you do the IF tube and the front end tube. Generally. Good. Oh, maybe this is the IF. This is the IF tube. This is the mixer tube, and this is the front end tube. Now the mixer signal comes in on 3. 3 would be the grid that's under control, and sure enough, there it is coming down to the ABC line. So these guys get their voltage from the ABC. Yeah, we can check that down the road somewhere. I don't think it's too important to check right now. I think we're gold. I think we're ready to do the alignment. That's what I think. Excellent. And I see from the clock upon the wall, it's 11 o'clock now, so I think I'm going to call it here today. I'm not going to do the alignment in the end. We're ready to do it tomorrow. I mean, that's a whole long process in itself. Got to have a little bit of a different headspace for it and everything. So thanks a lot for watching. Radio's really golden, I think. Fantastic. Have a great day.